Okay, for today's class activity, we're going to cover Chapter 12, Sections 5 through 7, and cover these concept questions and these exercises. Please go read the text to get familiar with the concepts and techniques, and come back to the video for guidance on solving problems. So starting with concept question 7. So this is a fun one. Well, suppose I am holding in my hands two identical looking spheres, and I tell you one of them is hollow and one is not, but they weigh the same, and otherwise you can't tell the difference. You can't cut them open. You can't just bang on them and see if one echoes. You have to do something mechanical with them. What could you do to be able to tell which one is hollow and which one is solid? Okay, so what is different about these two in terms of what you learned in the concepts in this reading? The biggest idea is that they have a different moment of inertia. Okay, I have a solid sphere. Is 2/5 times its mass times its radius squared. Whereas for a hollow sphere, is 2/3 times its mass times its radius squared. Now, we didn't need to know exactly these ratios. What we could say is, since moments of inertia depend on mass and where it's located, for a hollow sphere, assuming they're the same mass, it means all that mass is further away from the center of the sphere than for the solid sphere, whereas that mass is distributed from the center all the way out to its maximum radius. And so the hollow sphere is going to have a bigger moment of inertia because its mass is further away. More of its mass is further away from the pivot point, or the center of the sphere in this case. So because these are different, is there a way of testing this? That is from our Newton's second law for this problem, or for rotation. For rotation, we have that alpha is equal to the net torque, divided by the moment of inertia. Rotational acceleration, rotational force, rotational mass. So this looks the same as acceleration equals force over mass. Okay? And so if we put these like on a ramp or something, so that the force acting on by gravity is the same, because the mass is the same, then the one with the smaller moment of inertia will speed up faster. It will start rotating faster and faster, and therefore it'll roll down a ramp faster. And so since the solid sphere has a smaller moment of inertia, that means it's going to have a larger acceleration given the identical torque. And so we could say the one that rolls down a ramp faster is solid. Okay, that's a great application of these ideas. Number 8. Okay, I'm going to draw this, go try and solve this one. Pivot point, force, 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 double force, force. Okay, we have A, B, C, D, E, and F. Okay, so all those vectors are forces, and you're supposed to rank the torque caused by those forces. Okay, and the pivot point is right here. We're told that this rod is of length L. The distance from here to here is 1/4 L. The distance from here to here is half L. And all these vectors are applied at that one point. These A, C, and D are all applied at that point. Okay. So how would we calculate the torque of these? Well, first, torque is defined as the force times the distance times sine of the angle between those two vectors. Now, for all of these cases, the force is applied along this rod. The r vector is along the rod, either to there, or it's from here to here, or it's from here to here. So r is always pointing to the right, and then these forces have different directions. Okay. For A is pointing straight up, which means the angle that it makes with the r vector is 90 degrees. So tau A is F, that's a distance of L over 2, and then sine of 90 is 1, and so I just get FL over 2. Or what about B? Do the same logic with B. What do you find? Okay, B has double the force. Okay. but it's applied a quarter of the rod away, so L over 4, I mean, and it is also 90 degrees, so we get a sine of 90 is 1. All right, but that's 2 over 4 is the same thing as a half, so that's the same thing as tau A. What about tau C? Tau C, same force as A, same position as A, but it's applied at an angle this time. The angle between R and C is not 90 degrees, so I'm just going to plug in the sine of theta here, okay, to get the piece that's perpendicular. All right, and we don't know what theta is, but I know that sine of theta is going to be smaller than 1 because the angle is smaller than 90. So this is then smaller than tau alpha, or A. What about tau D? What can you say about tau D? It gives the same value as tau C. It doesn't matter what angle, they have the same perpendicular components. Okay, and that's all that this sine of theta is doing, is finding how much is perpendicular, and they have the same. So this is going to be the same thing, FL over 2 sine of alpha equals tau C, which was less than tau A. All right, now moving on to tau E, that is 2F, L this time, full length L, and it's also perpendicular. I should put equals in there. All right, so this is the biggest one, and I could have guessed that just by looking, big force, big distance, and it's perpendicular. That's what makes this the biggest. Lastly, tau F. Well, we've got this force. It's a single force. It's a total length L away, but it is parallel with R. So when I do sine of theta, this is sine of 0, which is 0. So remember, torque depends on how big of a force you apply, how far away from the pivot you apply it, and how perpendicular that force is to R. That's what the sine of theta gets us. Okay, so we're able to compute all those. All right, now let's move on to 9. Okay, so 9, we have a pivot with a rigid rod and a ball, and you push on this ball in that direction, such that you push on it just for a short time and get it to move. Now this is a horizontal circle, so there's not like gravity, it's not like a pendulum. This is a horizontal circle around some vertical pivot, so it's like a rod sticking up and it's spinning about that rod. All right. So with that in mind, is this torque a positive torque, or the torque caused by that force? Is it a positive torque, negative torque, or a zero torque? That torque would cause a clockwise rotation, which means this is a negative torque. Okay. Part B, after the push has ended, so you're not pushing anymore, what's going to be the type of motion that follows? So after you've finished pushing, is the ball going to speed up? Is the ball going to speed up for a little bit and then go at a constant rate? Is the ball just going to go at a constant rate? Is the ball going to slow down for a bit and then hold at a constant rate? Or is the ball going to just keep slowing down? Well, if this was pushing a box across the floor and I said after you finish pushing on the box, and this is a frictionless floor, what's going to happen to the box? It's going to just keep on going at a constant rate, because no net force means no acceleration, which means if it was moving after you finish pushing it, then it's going to keep moving. Same thing here. And so we have for B, it's just going to move steadily, move at a constant omega, constant angular speed. Now the problem states, I didn't state it in words, but it's a frictionless pivot. So that means it's has no loss of energy, no friction to slow it down. Okay, last one is right after the push is ended, is the torque positive, negative, or 0? So that one you should have guessed is 0, because when you finish pushing, there's no more force. There's no more applied force. Therefore, there cannot be another torque. Remember that to accelerate, there must be a net force acting on something. So same thing applies here. All of our arguments for F equals ma apply to tau equals I alpha. Okay, number 10. We have a ranking problem. So we have this one. So I'm going to let you look at the picture in the book. And so the question is the alpha. So alpha equals tau over I. Okay. We have to know, well, what is tau? Tau is RF, and they're all perpendicular, so these are purely just R times F. Since they're perpendicular, like we did over here, we have the sine of 90, which gives us a 1. So we have just R times F. Okay, but what is I for a particle, a distance R from a pivot point? That's just mr squared. Okay. So cancel out one of those R's, and we have F over mr. So that would be I alpha. Or, sorry, I apologize. Alpha A. That would be, because we'll use that as a reference. So what about B? What is alpha B? Well, it's twice the force and twice the mass. We have 2F over 2M times R. 2's cancel. That's the same thing as alpha A. Well, what about alpha C? We have twice the radius, but same mass, same force. So that's going to end up being F over M 2R, which is 1/2 alpha A. And lastly, alpha D. Okay. Twice the force, twice the radius, and twice the mass. 2F, 2M, 2R. 2 of the 2's cancel, leaving us 1/2 alpha A. So alpha A and B are the same, and alpha C and D are the same, but n equal to 1/2 of A. Right now 11. Okay, so I'm going to draw these. We have a solid disc with a rope tied around it. It's pivoted at its center along a horizontal axis so it can rotate, and there's this mass hanging on it that's free to rotate. There's no friction in that pivot. And then we have another one that's very similar, only it's got spokes, so it's the same mass, but all the weight's out here. So this might be a wooden disc. This might be a steel hoop, such that the masses are the same, but all the mass is located at the rim here, whereas the mass is distributed uniformly here. We have the same weights at the same positions, and they're going to fall to the ground. Which one will hit the ground first? What is the main idea to apply to this? Well, hitting the ground first means one of them is speeding up faster than the other, which is alpha. That's the angular acceleration. So which one has a greater angular acceleration? Well, it depends on which ones have a bigger torque and a smaller moment of inertia. Now, the torque's the same because the same mass is being pulled down on it. Okay, so the torque is the same. And so really, it's which one has a smaller moment of inertia, and that's the disk. Remember, this one, all the mass is far away, whereas much of the mass is close to the axis. So this is a smaller moment of inertia, so this one will fall faster. This one hits the ground faster. Great. Okay, so let's apply these to some numerical problems now. Let's take a look at exercise 18. Okay. Exercise 18 is a definition of torque. We've got a circle here with a radius of 2 centimeters. Note it gives the diameter of 4 centimeters, so you got to be careful there. We have a radius, and we have one force this way. We have another force this way. We want to find the net torque. How would I do that? Okay, well, I could say that net torque is going to be equal to, I'm going to have positive torques and negative torques. So let me ask this, is this one going to cause a positive torque by our conventions? This would cause a positive torque because it would cause this thing to rotate counterclockwise. So I'm going to have an F2R, and they're perpendicular because the distance from the pivot to where that force is applied is perpendicular to how the force is applied. So on a circle, any tangential forces cause a full maximized torque. Okay. Then I have to subtract F1 because if this one's going to cause it to go counterclockwise, which is positive, this one would cause it to go clockwise, which is negative. So it's going to be negative F1 R. It is also perpendicular. If I draw a line from the pivot up to where the force is applied, those are perpendicular. So plugging in my numbers, I'm going to get the F2 minus F1 times R, which is 20 minus 30 times the 0.02, and that gives me a negative 0.2 Newton meters. It's negative because this one's bigger, everything else is the same, so that's going to have an overall clockwise acceleration. Okay, apply the same ideas now to number 19. So look at number 19. Okay, here's number 19. So these forces are equal, and we're told that there is a net torque of 5 Newton meters. We're given that this is a square of 10 centimeters to the side. What is the size of the force that would cause that? Well, it's the same principle as this. We have a net torque. We know that number. We're told that that's 5 Newton meters. Okay, and that's going to be equal to the contributions of both of these. So let's look at this one right here. This one has a force F. It's a distance R away, and they're perpendicular. So here's that R, and those are perpendicular, so it's just F times R. Okay, now that's going to make it rotate counterclockwise, so that's positive. Now let's come to this one. How much torque would this one cause? It's of size F. It's a distance R away, but R points from here to where the force is applied. What's the angle between those? It's 180 degrees. And sine of 180 degrees is 0. That's not going to produce any torque. Now remember, we came up with that math to help us make sense of reality. This would make sense without any math. I don't have to do a cos or sine of theta. Okay, this is pushing straight at the pivot point. That's not going to cause this thing to rotate. I need to have it pointing somewhat perpendicular to the pivot point to get it to rotate. So I can just ignore that one because it's pointing towards the pivot point. Like this one over here, this is pointing away from the pivot point, and it's not going to make this thing rotate. So that would cause 0 torque. So it's just F times R. And so solving for that force, tau net over R, you're going to end up with 50 newtons. All right, 24. Okay, so this is a definition of using our Newton's second law in rotation. So we're told a moment of inertia. We're given moment of inertia, 2 kilograms per meter squared. We're told the angular acceleration is 4 radians per second per second. That's the rate of change of angular velocity. What is the net torque? Okay, well, we can just use our definition of Newton's second law, which is tau net equals I times alpha. Okay, we're given I, we're given alpha. We just combine the two, multiply the two. We're going to end up with 8 Newton meters. 8 Newton meters. Okay. Now I want to emphasize that that is correct units with this being in radians per second, because torque is a Newton meter, and this is a kilogram meter squared, and this is a per second squared. So this is a kilograms meter squared per second squared. And a Newton meter, well, a Newton is a kilogram, because a Newton is mass times acceleration, which is kilograms meters per second squared. And then we multiply by another meter to get squared. So those are the same units. Okay, lastly, 27. So 27, we have this compact disc that's 12 centimeters in diameter, and it speeds up. It speeds up from rest to its final operating speed of 2,000 RPMs, taking 3 seconds to do that. The disk's moment of inertia, so we know its moment of inertia, is 2.5 times 10 to the negative 5 kilograms meter squared. Very small, but it's also a very lightweight, small disk. And so the question is, how much net torque is applied to the disk? Okay. So that's the same thing as this. It's just now we have to use kinematics to figure out alpha. Okay, we know I, so tau net equals I alpha. And I was given alpha is just simply our change in angular speed over our change in time, which we're given. Now this is in revolutions per minute, so we need to convert that to radians per second. But if you do, converting the 2,000 to radians per second and then dividing by the time, you get this being 69.8 radians per second squared, which is now in the correct units. And by multiplying that by the given value for I, we get a torque of 0.001745. That's probably too many digits, but I'll just list it out. Newton meters. Right? Or 1 millinewton meter. We could write. Now this has a part B, and the part B is just a review of kinematics, which we've done before. So I'll pause on that one.